All right, here we go. Now we're going to start talking about doubling time and half time or half-life or halving time is what we'll call it too. So this is section 8B, and so let's jump right in. Okay, so doubling time. So doubling time is the amount of time that it requires for an amount to double in exponential growth. Okay, so again, this pertains only to exponential growth when we talk about doubling time. And the halving time is the amount of time that's required to have half of what we started with. Okay, so that's with decay. So when we talk about exponential growth, we'll talk about doubling time. When we're talking about exponential decay, we're talking about the halving time, or when we're talking about radioactive materials, we call it half-life. All right, so now after a time t, an exponentially growing quantity with a doubling time of t sub d, right, increases in size by a factor of 2 raised to this power. Okay, so if you notice, the base is 2, okay? The amount of time that's passing is the lowercase t, and then of course t sub d is the doubling time. So basically what this exponent here is telling us is how many doubles we have. So we're taking the amount of time that passes, we're dividing by the doubling time. So in essence, that exponent is representing the number of doubles, okay? Because that's how many times we're gonna take the 2, right? The base, the factor of 2, and multiply by itself that many times, okay? So the new quantity, so if we put this in a formula where t equal to 0 is the initial starting time, okay, and we have an initial value at t equals 0, this would be the formula that will tell us what the amount we have after time has passed, okay? So we're going to take this factor and we're going to multiply it by the initial amount or the initial value that we have, and that will give us the new amount or the present value. Okay, so this is one of the formulas that we're going to use. So now, here we're going to talk about compound interest, right? So this goes back to our section on Unit 4. Okay, so now it says the compound interest exponential growth because it is interest-bearing account that grows by the same percentage each year. We talked about that before. Suppose that your bank account has a doubling time of 21 years. By what factor does the balance increase in 50 years? Well, the factor is going to be the 2, right? So the factor is going to be this, the 2 raised to the t over t sub d, right? And so in this case, the factor is going to be 2 raised to what? 50 divided by 21. And so that's going to be a factor. Of course, we can put that in our calculator and calculate it. Okay? And so we get approximately 5.21. That's the factor, right? So your money is going to grow by a factor of 5.21 over 50 years based on the doubling time of 21 years. So if you have a balance of $1,000 in 50 years, you'll end up with $5,210. Now, for a quantity that's growing exponentially at a rate of p% per time period, the doubling time is going to be approximated by this rule of 70. Okay, the rule of 70 says just take the interest rate as a percentage and divide it into 70. And that gives you the approximate time it will take for the amount to double. Okay, now this is approximation, and it only works best for small rates of change, so small growth rates. Okay, so this will break down over about 15%. If the rate is at or about 15%, it's not going to be accurate. Okay, there are other rules, like we could use the rule of 72 that I use in finance, or have used in finance. And again, these are approximations that are only good for certain growth rates. Okay, now here it says the world population doubled in the 40 years from 1960 to 2000. Okay. What was the average percentage growth rate during this period? Contrast this growth rate with the 2012 growth rate of 1.1% per year. Okay. Okay, let's look at this. Okay, so 1960 to 2000. If we look at the rule of 70, we take the growth rate, right? And we can solve for percentage. We can solve for the growth rate, okay? It's telling us the amount of time it took to double. So we can use the rule of 70 to also solve to get an approximate growth rate, P. So if we plug in our values, we get 1.75% per year is what we get. Okay, so that was not bad at all. Okay, now the average population growth rate between 1960 and 2000 was about what? 1.75% per year. This is significantly higher by 0.65 percentage point, by almost 2/3 of a percentage point, than the 2012 growth rate of 1.1% per year. Okay, now let's talk about half-life. Now the only difference when we're talking about half-life and using halving time, the only difference is the factor. The base that we're using is a half instead of 2. So doubling, we use 2. For halving time or half-life, we use a half. So that's the only difference in the formula other than the half-life or the halving time. Okay? So everything else is the same except for the base. And instead of T sub D, we use T sub H. Okay, so let's look at radioactive carbon-14. We know that it has an approximate half-life of 5,700 years. It's actually closer to 5,730. But anyway, we'll use 5,700. It collects in organisms only while they're alive. So while we're alive, we are collecting carbon-14 in our system. When we die, we stop producing carbon-14, and it starts to decay with a half-life of 5,700 years. Now, it says, what fraction of the carbon-14 in an animal bone still remains 1,000 years after the animal has died? Okay, now, let's look at this. So, it dies, right? So we can look at the percentage of carbon-14 that is in the bone, right? So if we look at this, okay, the half-life is 5,700 years. So the fraction of the initial amount remaining after 1,000 years is given by this, right? So if we use this factor, right, just like we did before, we're going to take the time, which is 1,000 years, divide it by the half-life or the halving time, and we get 0.885. Okay, so what does it tell us? That tells us that 88.5% of the radiocarbon-14 is still there. So in other words, if we have a 1 kilogram, if the bone originally contained 1 kilogram of carbon-14, after 1,000 years there'd still be 0.885 kilogram still remaining in the bone. All right, now let's look at plutonium. Plutonium-239 has a much different half-life, okay? So if we have 100 pounds of plutonium-239 and is deposited in nuclear waste site, how much of it will still be present in 100,000 years? Well, let's look at the half-life. The half-life is 24,000 years for plutonium-239. So if we have an initial amount of 100 pounds, then all we have to do is use our formula and plug and chug. So we know the initial value, which is 100 pounds. We know the amount of time that passes. We're saying 100,000 years. And we know the half-life is 24,000. So all we have to do is plug our values and use our calculator. And so after 100,000 years, we will have about 5.6 pounds of plutonium-239 remaining. Which makes sense, right? Because if we're, so this goes into 100,000 approximately 4 times, right? So if we have half of 100 pounds after the first time, right, that's going to leave 50 pounds. And if we, the next halving time we'll have 25 pounds. The next halving time we'll have 12.5 pounds. And the next halving time is we'll have approximately 6.25 pounds. So, and since this is a little bit more than 4 doublings, it makes sense that it would be approximately 5.6 pounds. Just saying. It makes sense. All right, now, the half-life formula, by the way, is exactly the same as the doubling time. So the rule of 70 is exactly the same, whether you use it for half-life or you use it for doubling time. Okay, it's 70 divided by the percentage rate of return, or growth rate. Okay, and again, it doesn't work for anything around 15% or higher. Okay. Okay, now let's look at the Russian ruble. It says here that it's due to the inflation. Suppose that inflation causes the value of the Russian ruble to fall at a rate of 12% per year relative to the dollar. At this rate, approximately how long does it take for the ruble to lose half its value? So we're looking for the halving life. So again, if we look at 12%, right, that's the decay rate. So we're going to take that and we're going to what? We're going to find the half-life, and we're going to take 70, and we're going to use the rule of 70. So if we take 70 and divide by 12, okay, we get approximately 5.8 years. Okay. So the ruble loses half its value against the dollar in approximately 6 years. Now, what if we want to know the exact doubling time and half-life? Well, here are the two exact formulas, and these involve logs, okay? So the doubling time is given by, again, by the way, we use R, which is the growth rate, as a decimal, okay? So we take the percentage and divide by 100. So it's always as a decimal, not as a percentage. So in the doubling time, it's the log of 2 divided by the log of 1 plus R. Okay. Now, the only difference is with half-life, we use a negative sign out front. Okay. And again, I could show you how to derive that, but it's basically because we're using the log of a half, we get a negative sign. Okay. So again, and also because the rate is negative. Yeah. All right, so here we go. Now, again, depending on the situation, be careful. Make sure you read the problem carefully because you may have to use one of these two formulas if they're asking for the exact half-life. Okay. So it says the population of rats is growing at a rate of 80% per year. Find the exact doubling time for the growth rate and then compare it to the doubling time found with the approximate time formula. Okay, so here's where we're going to use the formula, right? So we're going to use the exact formula for the doubling time, and that's going to be equal to the log of what? It's going to be the log of 2 divided by the log of 1 plus r, where r is equal to 0.8. Okay, and then literally that's all we have to do is plug. Now, by the way, on your calculator, if it doesn't show the 10, it's a base of 10. If it doesn't show that, it's assumed to be 10, so it's a common log. Okay. Okay, so if you plug it in, you get approximately 1.18 months is the exact doubling time. So a little over a month. Okay. Now, the approximate doubling time, if you use this, the general formula is 0.87. Notice a huge difference. But remember, the rule of 70 only works for small growth rates. Anything around 15 or higher is going to be unreliable and it's going to be way off, as you can see in this example here. So again, always pay attention to the growth rate that you're given when you're using the rule of 70. All right, that's it. You guys have a great day, and I will talk to you soon or see you later. Take care.